Well, hello everyone, and welcome to It's Not Your Parents' HTTP session today. You look like a bunch of very smart and handsome developers, completely immune to flattery, and I'm really happy that NDC invited me to talk about this topic. It's a beginner-level topic, so I'm not going to go into details of HTTP frames, for example. But we're going to overview the history of HTTP, what problem it was trying to solve, where it's now, today, and what the future is for HTTP and alternatives. A couple of words about myself first. Where is my... So my name is Gleb Bahmutov. I started as a computer vision researcher, and then I slowly switched into web development. I'm very active on Gitter and GitHub and Twitter, and all the slides will be on slides.com. I made a transition from being a C++ and C# developer for a bunch of years to CoffeeScript and then JavaScript in the front end. But my passion is actually writing things down for myself. Right? If you attended Troy Hunt's presentation, Hack Your Career, it's like the first point that he made is like he made a blog. And he was just trying to write things down for himself so that he doesn't have to look up things everywhere. And the same is true for me. I forget things, and in order not to forget, I blog. And I recently took a screenshot of a word cloud of all the things that I wrote about on the blog, and JavaScript, functional Node.js performance. I don't have HTTP here. I do have browser as a tag, but nothing related to HTTP, right? But I think I know what I'm doing, right? Like I have my sleeves kind of rolled up, so that means I'm in business. My proudest achievement was writing a little code snippet for playing Game of Life on GitHub contribution account. So you can go to any account and just click the button, and you can see if you can get a repeating pattern. Some people have beautiful, visualizations. Most people's accounts kind of die after a certain number of iterations. I was born in Moldova, but I don't have to tell you guys where it is, because we're in Europe. You guys know where it is, probably. In America, I have to explain where Moldova is. Right now, I work and live in Boston, which is in Massachusetts. I live in Cambridge, the home of MIT and Harvard universities. And I was looking at a bunch of jobs that I had before, and there was one thing that kind of underlined the common theme, so to speak. And it wasn't a programming language or a subject. It wasn't a particular technology, except for one thing, and that thing was internet, right? None of these companies would be where they are today, except for probably MathWorks. But even at MathWorks, I was actually porting MATLAB to run inside your browser without internet. And we associate, World Wide Web, like whatever we see in the browser, with internet. When people say, I saw it on the internet, they mean I saw it in the browser. And if you say, I saw it in the browser, that means HTTP. So none of these jobs, that are very different, would be possible without HTTP. So, well, today, I work at a company called Cypress, and we just do end-to-end testing tool. Looks like this, where you load your website, and it runs right inside your browser. So you can see the execution running. It completely replaces Selenium and Protractor and Karma and Phantom.js. And then you can just go through each step, and you can see exactly what browser did. We're trying to solve a problem that, when we say internet is broken, we mean websites are broken. There's so many crappy websites where I cannot buy a ticket when I want, where I'm trying to make a reservation, it doesn't work. So we're trying to solve it. OK, so 2017, I called myself a software engineer, right? That's kind of my day-to-day state of mind. Like, I constantly look puzzled, and I constantly hit problems. And I'm not sure about you guys, but I often ask myself a question, right? If I wasn't born in 1980, if I was born in a different time, what would I be? What kind of job would I find myself interested in? So let's say I was born 4,000 years ago. I probably would be a farmer. just by statistics, by probability. Most of the people were just subsistence farmers. They grew their own food, or they hunted. And I probably would be a farmer. I probably would be a very happy farmer like this guy. This is a weird picture. I don't know why he's so happy. But if I were born along the Nile River 4,000 years ago, I would probably want to be a civil engineer, right? Because they had a large project building a pyramid. So, royal family would come to me, or my company, my corporation, and would say, OK, we need something that would look good after the pharaoh dies, and it would look good on a greeting card 4,000 years later. And I was like, oh, well, I'll take whatever technology is available, plain, simple geometry, stone materials, unlimited labor, very cheap labor, and I could probably build you something that looks like a bunch of bricks stuck together, right? And I would build the pyramids. And I know that I would like that job just because my son and I, we build things from Lego. And the first thing that we do is like, how tall can we build a tower from Lego blocks? And we first build a tower higher than me and taller than me, and then all the way to the ceiling. So I know I love building tall structures from bricks. I want to be an engineer, even if I were born 4,000 years ago. So the word engineer is actually a pretty good word. It's derived from Latin, from two words. And one word means to devise or construct. And another one means cleverness. So an engineer is someone who builds something in a very clever way, right? But in our viewpoint is that an engineer is someone who has to construct something, but in a set of constraints. And constraints would be features, time, cost, user experience. For example, if you're constructing a pyramid, you probably are not concerned about the costs, but you're concerned about the feature. That thing has to look good, because otherwise you probably will die. You can also think about engineers as a link between science and what is possible and the general population. So an engineer can build an airplane, right? Something that operates on scientific principles for general population to take flight. If I were born in Roman Empire, this is a golden age, right? I would be building roads, I could be building aqueducts, coliseums, palaces, temples. Civil engineers in the time were, I think, in a very good position, but nothing like industrial age. If I were born 200 years ago, I probably would work on hydropower plants, steamships, railroads, building bridges. But then if I were born 60 years ago, I probably would want to be a scientist, right? Because at that point, especially because of space race, being a scientist was the pinnacle. There are different levels of, let's say, respect that society pays different professions. Doctors are always admired and respected. In Soviet Union, for example, where I was born, being a scientist was the top, right? Because you could be a celebrity, you could be a doctor, but being a scientist was the highest position that society admired. Except science is actually hard. In science, if you ever look at a paper, a published paper, there is always a last page. And the last page lists all the references, all the source material that this current page uses to actually propose something new and describe something new. And as Isaac Newton said, that it's not that he was taller and he could see farther away, but he was standing on shoulders of giants. So in a sense, we're still building a pyramid, except now it's not made out of big stone blocks. It's made out of our inventions. So every scientist takes whatever other scientists created before, cites their work, and then publishes new paper. And if you don't do this, then your career goes nowhere very, very fast, right? Science is a constant grind of trying to publish, trying to get your paper in a top journal or conference, getting tenure, right? And this means that scientists constantly have to look up source material, right? And they have to make whatever they produce. It could be papers, images, experiment results, raw data, as available to others as possible so that other people can cite and reference it. And that your science becomes more important. If more people link to you and can use it, then your career prospers. But you also have to do it constantly, right? Yourself. You have to cite other people's work. OK, so what does this have to do with HTTP and the topic at hand? OK, moving to Europe. In 1989 at CERN, a couple of thousands of scientists are working there, and they have this problem. They have a bunch of papers. They have a bunch of data sets, right? And every scientist is trying to find information or provide information to others, right? So they have this giant number of documents, and they have no idea how to find them, how to retrieve them, how to search, how to store them. OK. At that time, they had hired a permanent researcher by name Tim, and he was there for, I think, 8 years by then. And he has this problem, and he says, well, I'll try to come up with a solution. OK? And he makes this proposal, and it goes to the management, and it's titled Information Management, a Proposal. It has an abstract. It kind of describes a graph of documents and how they could be connected to each other. And on the top, it's kind of hard to see, but the response from his boss when they read this proposal is vague but exciting, right? So talk about setting the bar very low. Kind of like, I want to invent the internet, but exciting. So he goes off and starts working. At that time, he already wrote something called Enquire. And Enquire dealt with, it's almost like a wiki of cards, right? And the cards were written in something called hypertext. Basically, it's normal text, but they had almost like a markdown, a link with like name of another card that you should look if you want more information. And it wasn't the only proposal, right? He also considered other things for linking a bunch of documents. For example, he thought about doing keyword search, right? Every document would provide a list of keywords, and when every time you need a document, you would search by keyword, and maybe you'll find the document and related things. He thought about maybe creating almost like universal Dewey Decimal system, like libraries use today, but for documents. Then he said, no, I'll just have this giant graph. Any document can link to another document using some resource ID, and the document could be on a different server. By that time, there were already servers, like FTP, that could actually serve you the document, right? But there was no concept of connecting hypertext to those servers. So off he goes, and 2 years later, he comes back and he describes what HTML is, a markup language, and he builds HTTP server, and he also builds the first browser. And this is the screenshot of a first browser called World Wide Web, all one word. There are a couple of interesting things if you look at the first browser. First, there were a bunch of spelling errors, right? It was very quick, right? He had to write all parts of the system, so sometimes spelling takes a backseat. Second, it kind of looks like a modern thing, right? He used Next system, which kind of led to Apple. So the dock bar on the right looks the same. Interesting enough, if you think about it, right? Imagine you're starting a library and there are no books, right? the first thing a library probably would provide you is like a stack of paper. You want to have a book to read? You have to write one. So this means that on the left, you have a main menu. There is edit button, and there is find button. And the edit is actually above find. This browser functions both as a browser and as editor. And the editor function was actually first, because most people had to actually write something before you could actually read something. Over time, we obviously switched to more passive. I'm just reading whatever is in the document. I'm producing very little content. But the first browser had edit and create on the top. And obviously, you edit the document that you store locally, right? You can just access the file system. If you want to find something, you have to go to remote server, and then it's read-only. This also had a very interesting model of interaction. So usually, we think about user-centric browsing, right? We go to a page, it has a link. We click on the link, we go to another page. When we click previous or back button, we go to the back document that we actually saw. So the user controls what back and forward means. In this browser, you had two modes. You had user-centric, but you had also document-centric mode, where imagine a document has a bunch of links. And you go to the first document, click on the link, and then you click a back button. Instead of you going back to the previous page that you saw, it actually opens the previous link in original document. So previous and next were actually defined by the order of links in a document. So it was document-centric browsing, not user-centric. And this was meant for quickly going through all the links in a document. Because obviously there was no spam, there were no ads. You could just read one link after another. So this was 1991. 94, a second version called Nexus was written by him, and this already looks just like a modern browser. It actually has a first domain, info.cern.ch. By that time, the DNS system already was available. And there were already domains, but they were only, they were not World Wide Web. They were FTP direct connections. This was first website on the first modern domain. There was no URL still, right? You did not see the URL. If you wanted to actually see the URL, you had to open inspect mode and actually see what you're looking at. The first website actually just described what the system was. What's hypertext, HTML, right? How to edit, who are the people behind it, and it also switched the order of edit and find to find and then edit. More in tune with just passive browsing. So this was the user-facing, but under the hood, you had to retrieve the remote documents. It's easy to retrieve local documents. You just open a file, you read it in, and you display it. But most of the links actually pointed somewhere else, right? That was the original goal of the system. So you needed a way to actually transport that HTML document, bring it in order to show it. So you needed a protocol. So 991, Tim Berners-Lee describes HTTP. He's part of document retrieval. And it's known as HTTP.9. And as you can see, it's not a very large document. It's signed by Tim BL. And I talk about being an engineer, right? An engineer is someone who considers costs and trade-offs and user experience and practical application of a technology. This guy is engineer's engineer. I mean, his title right now is Professor of Engineering in the School of Engineering with a joint appointment Department of Electrical Engineering. So his title has 3 engineer words in it. Like, if you want to be an engineer, that's your role model. But another important thing is that the whole proposal, the whole standard at that point, the initial thing, was only 650 words. It fits on a page and a half. It's that succinct. Because when you're trying to find the trade-off between the features, the cost, the time, he needed something now. He didn't have a bunch of years. He wanted to have a system, and the system of a browser, HTML, but no way to actually retrieve a different HTML document was useless. So he needed something very, very quickly. And so he concentrated on simplicity. There are only 4 sections in this document. You have to open a connection, you have to make a request for a document, you have to receive a response, and you have to close the connection. That's it. The simplicity rules. You know, people ask, why is it port 80 by default? Well, because he picked one. And at that time, there was RFC of commonly used ports. And they covered a bunch of ports, right? And at that point, there was a gap between 79 and 81. So he just said, OK, I'll take that one, seems free. And there are other gaps. So we might as well, we could have had a port 63 or 41, whatever. There are a bunch of gaps. But he picked 80, and it became the default. He specified that once the document has been transferred, the TCP connection is closed. Right? So that kind of defines the current HTTP model before we actually extended it. But it was a single-shot operation. Give me the document, and when you give me the document, I no longer need you. Free to break the connection. You can serve some other request. The whole thing was just get and the name of a document. Right? Looks very, very similar to what we have right now, except there is no host name. Just get and the name of the document. Again, simplicity is the key. At that time, the only thing that the browser could show was HTML, the standard that he invented, right? And it's an ASCII-based standard, and that's it. There is nothing else. And as soon as you send and receive this ASCII text document, you close the connection. The only kind of interesting thing is that if you engineer, right, and you devise a system, you probably want to do some, I guess, safety standards or guards, or describe unhappy path when how to do something when what's the behavior when something fails. And in the first version of HTTP, there was none. You receive a document, and the server could not tell you even if the document was not found. The server could send HTML, and it would include a text not found. But there was no way for machine to actually communicate for protocol that the document doesn't exist. You, as a user, and at first it was all meant for humans, right? Human would read it, oh, I guess the link was wrong. Or I guess the server is not doing its job, or I guess I'm not allowed to do that. No. You have to read the text. There is no error response code. No response code at all, not even 200. And at the end, the protocol says the server will not store any information, right? It was purely read-only request. No cookies, no sessions that we make on top of cookies, no post requests, nothing. It was purely read-only document retrieval system. And I always think about this, and we have a name for this pattern, right? And it's, you're not going to need it. Like, why spend time thinking, coding, debugging, arguing about features that you're not going to need? I have an immediate goal. I want to retrieve all the textual documents, right? And I'm just going to implement this. Does HTTP solve this problem? What is this problem? Well, I'm reading this document. It has text, and it has a link, a hyper, ref, href. Goes towards a different server, has a name, and I want to read that link. That's the problem that HTTP is trying to solve. We always forget when we say, oh, HTTP is slow, or HTTP doesn't do that, doesn't allow two-way communications. Well, it wasn't meant to do that. HTTP stands for Hypertext Transfer Protocol. It transfers you the HTML document. That's it. It's like arguing why doesn't Honda Civic, why can't it transport 10,000 people? Well, it's not built to do that. The user asking for document and receiving another HTML document. When you do that, right, when you actually try to retrieve something from a document, you have to transfer data. And at that point, you had a choice. What actual transport protocol am I going to base HTTP on? And the decision was made because you don't want to lose part of a document, you want to retrieve a whole document, and you don't want to implement the logic itself to pick the TCP, right? Transfer Control Protocol. And we kind of think about us going through a browser that it just does the direct connection, but it's not true. The actual HTTP request goes to TCP, that goes to IP, that goes to our cloud, and then through the same mirror stack on the server, gets to the HTTP server, which returns the document. To us, all details are hidden, but different layers actually ask different questions. Like IP, for Internet Protocol, asks the question where. Where should request be delivered? And TCP just says how. I have to transfer first part, second, and then assemble the thing. The choice of TCP has a huge implication, right? Because the performance of HTTP retrieval, and in the future other stuff, is directly tied to performance of TCP, and we will see this over and over again. TCP has two things going for it and making it an ideal choice. It's guaranteed data delivery, right? If you're asking to get HTML document, you will receive a full document. There will be no parts missing. And most importantly, nothing will be garbled. It's not like the first paragraph will arrive after the second. The first paragraph will always be delivered before the second one and assembled in the same order as the original document. And I personally celebrate that. I think the trade-offs and the original system was a great, simple concept. The whole IT boom of 2000, the internet boom and bust, right, would not have happened if this technology wasn't clever enough, ingenious enough to be extendable and powerful. Interesting thing, in a protocol, the third sentence says future HTTP protocols will be back compatible with this protocol. Obviously, this kind of got dropped really quickly, saying like, no, we have to support more than what you give us, so we're going to skip that requirement. And 1991, it's not that long ago. It was only 26 years ago. Now, here's a question. Would you get on an airplane if 26 years ago airplanes looked like that? Right? Obviously not. Like, no way the airplanes could have evolved that quickly in such a short amount of time. But internet did. The growth of internet was incredible. First, just academic institutions, but quickly businesses picked up that retrieving any text over the internet system is actually a very interesting proposition. And the number of available websites, not servers, but websites, grew at extreme rate. As soon as many people started using the system, you get the question of, OK, I want to see this JPEG. How do I do that? And turns out, a lot of things that we thought were not needed were actually needed. So fast forward 5 years, the second standard, HTTP 1.0, is already at 60 pages, and it kind of looks like what we expect to see. It has cookies. It has request headers, response headers, and so on. That's kind of useful. Non-HTML data, images. More methods were added. It's not just get, it's also posting the data, the main change. Status codes were added like right away. And user preferences, like you want to communicate what format of a document and what are your human characteristics were. A few later, because of great competition and because of a great browser wars, there were a lot of other changes to HTTP1. Right? 27 drafts. Most of them concentrate on performance and security. As soon as many people got on the internet, you had to take care of things that were not as simple. Let me see. I'm going to skip IETF, but let me just go to the next one. We think that HTTP1 is kind of uniform, and all the details are taken care of for us. But in reality, it's a mess. It's a mess of protocols, implementations, extensions, non-standard parts, and they all interact. And I highly recommend you pick up this book, right, that shows the tangled web, how different things interact, and security implications of the interaction. But we're still asking for a page, and the browser goes and retrieves the page. And I'm talking about the browser. I know the servers also communicate for HTTP, but most of the things apply. And in a browser, the choices are limited. On a server, you could do TCP connection directly. In a browser, you have to work with standard. The modern HTTP request and response that used to be so simple kind of blew up, right? We have giant amounts of information flowing with HTTP through each request. State, even though protocol was supposed to be stateless, is transmitted for cookies, we have cache, and we have a lot of security headers, things that were missing. As soon as we got to the whole page retrieval, we started asking, OK, I don't need the whole page. I just need a part of a page without reload. So Internet Explorer introduced a feature of including a frame in one document that comes from another HTTP server. So already you have a website that's a composition of a couple of things. And then they quickly introduced something that's scriptable, the XMLHttpRequest, AJAX as it's known. And it actually went very quickly from being just internet only to showing its full potential when Gmail got introduced to RFC standard. The code kind of looks nasty. I don't like making direct requests, but there is a new standard that tries to normalize how browsers retrieve different pieces of information. It's called fetch. It's quickly being adopted. I think all the modern browsers, except from, I'm not sure about Safari, but probably it will support it too. But it's very clean syntax, and it's available already. So today, what do we have? We have the whole stack HTTP, and then on top we implement something else, like REST, GraphQL, again, trying to make it more usable, trying to build up the list of features. But if we talk about HTTP, it's transitioning to HTTP2 or Quick, but there are a couple of other alternatives, right, that are available today, like WebSockets, like WebRTC. And unfortunately, even though I like WebRTC technology, I don't think we have time to discuss it. But I'll speak a couple of words about ServiceWorker. OK, so that's the outline. WebSockets. Making TCP connections is incredibly expensive. You have to handshake. That requires a couple of round trips. People try to optimize it, but still, the round trip is killing you. Every request, because only one thing can be done, requires this. The congestion protocol tries to say, OK, you don't know how much data you can send, so you kind of try to do a slow start, and you send more data, and if it doesn't get through, then you go back to previous level. Again, it's very slow. HTTP connections are expensive, and especially if you can only do one, that's very bad. HTTP1 defines how to upgrade. So you connect to HTTP1, and you want to say, OK, I want to switch to something else, and if the server supports it, then you both can switch. And it's actually very nice, right? That's a good feature to have. WebSockets got implemented pretty much immediately, became a standard, and now every browser supports them. So if you want to avoid the overhead and you want a single bidirectional connection in a browser, WebSockets is a way to go. For ServiceWorker, all the major APIs are now require HTTPS, right? Because the APIs and the amount of data that they can transmit and amount of things they can do on your behalf as a user and on the behalf of a website is tremendous. So you better be pretty sure that you're actually talking to the right website and no one actually impersonating you. So the best things are HTTPS now. For example, ServiceWorker is trying to solve this problem, right? It's not HTTP protocol, but it works with intercepting HTTP requests that coming out of your browser. And it's meant to solve this problem of application cache. When things go offline, when the server doesn't respond, what do? We tried kind of write down all the things that browser should cache, but it never worked. So we had to switch to using something else, and that was ServiceWorker. So a browser has this new thing that kind of sits in between the browser and can intercept every request, can transform it, send it to the server, and can receive a response, transform it or not, and give it back to a browser. And you can implement all sorts of smart caching strategies, offline support, you name it. In these slides, there are a bunch of examples later that you can look and videos where things look like they shouldn't work, but they still do, just because of ServiceWorker. Before I discuss HTTP2, I just want to address the overflow room, right? Because that's the most important part of the talk, right? And if you guys are watching, you probably should switch. Like, don't even switch the audio, just look at the slides. OK, HTTP2, the only purpose of HTTP is to make things faster. And things are slow right now because if you look at how it's playing on the wrong screen, how even a simple website is loading its resources, right? So I'm reloading NewYorkTimes.com. You can see hundreds and hundreds of requests going out. All sorts of things. Page, scripts, styles, fonts, ad tracking technology, everything. 236, 246, 250. This looks nothing like the original page, right? Completely different problem. HTTP doesn't tell you how to do these things quickly, right? 200 things to fetch. How do I prioritize? How do I fetch the right thing? So we quickly found out that the limitation is not the bandwidth. As you scale up the available bandwidth for a mobile device or for a laptop or for wired connection, the page still loads in the same amount of time with HTTP. What really kills you and what makes the biggest difference is making the round trip shorter. It's the delays to make each connection and fetch the data that really affect the loading performance. So in 2009, Google started Speedy project. And Speedy was trying to reinvent HTTP. And it was a binary multiplex protocol, and immediately they saw like 50% improvement. So they kept working on this, and 6 years later, it became an RFC. And that's what we know by HTTP2. And the changes were purely in the way things were sent. Nothing in the API changed, except for one thing. So it's a level that kind of sits between the application, the browser, and everything below, and it converts what we know as text request and response to a bunch of frames. So splits them up, sends them individually, makes the frames binary. Now you can do things like that. You need a bunch of resources? Well, split everything into frames and use a single persistent connection to send things. And you can multiplex. And so multiple resources will share it and arrive at the same time And then HTTP2 will reassemble everything and give you complete things correctly. You can even specify dependencies and say, hey, give this resource a priority by giving weights. So for example, in this case, I need two resources, A and B, and I say, well, give A 12 slots and B 4. That means that A will use 3 times as many frames to be fetched than B. So it should arrive 3 times faster. You can say, fetch D and then C. And in the last example, you can fetch D, then C, then fetch A and B, but give A 3 times as many free slots as resource B. So that makes things a lot more controllable, a lot faster. And the things should arrive in a better order. The page should arrive first, and then maybe some splash images at the very end. If you ask GitHub for its headers, it will give you this. And the whole amount of security and content security policy is just ginormous. And that's why a single request, the cookies and header, take up almost half as the original protocol definition was in 1991. So the big part of HTTP2 is to compress the headers. And they do it by 2 things. One, they only send you the diffs of headers. So you have request 1 and then request 2. The only thing that really changes is the URL, the path, if it's on the same domain. And so the protocol will send a header frame with all the headers, but with the second resource, it will only change the change path, just a single field. Also, you can see the columns in request. Because HTTP1 used to just specify the full URL when it was making a connection, so you never had actual headers for get, for method, for host, for path. Now they have to be specified, and they're called pseudo headers, and now they can be sent separately. And also, it has a static table of all the common headers, like method and refer, right? And you can just encode this by numbers, by indices, instead of sending like refer text. And everything else is encoded as well. Pretty good adoption. All the evergreen browsers now support it. So in just a few years, HTTP reached a lot of traffic. It's actually hard to find up-to-date stats. And you would think that major CDNs or proxies or websites would make this data up-to-date and live. So the best I could find was June, but it only said 14% of all websites were using HTTP2, right? And this is growing. This is doubled from previous year almost. There are a lot of websites that are kind of stuck in between on Speedy protocol, and they haven't made a transition, but HTTP2 really optimizes the number of connections. So a lot fewer requests are now using just one connection and then saying, that's it, I don't need any more. 2 great resources if you want to find out more about HTTP and networking are available online for free. Ilya Grigorik, his browser networking is just unbelievable book. And Daniel Stenberg, the guy who wrote curl, has a free online website that actually explains in human language HTTP2 protocol and what different parts mean. If you go to Chrome Net Internals, you can actually inspect HTTP2, and you can see individual frames as they arrive. I'm going to skip it just because of time constraints, and I'm going to go to something else. So I said that HTTP2 was one-to-one replacement of HTTP1. Nothing new, right? You just change the framing before it goes to TCP. But there is one addition, and that addition is server push. Imagine you're a client browser, and that's a timeline, and the server has a document, and you say, give me the index.html. You receive index.html, you parse it, and you find, oh, there is, an image. So you make request for an image. The server gives you the image, and then you display it. Well, it kind of takes a long time, right? How do you optimize this time between receiving index.html and then showing it? Not even when you make the request, but actually the longer line. Who knows that you need the image and index.html? The server. So with server push, you make a request, and the server says, OK, you need the index.html, but you will also need this image. And I'll start pushing it right away over the same connection. And so you receive it index and image. You parse the index.html, and you're like, I need to get this photo. You make a request. You still make a request. Nothing changed. But then you immediately hit the cache and says, I already have it. So it should be, in principle, faster. It's extremely nice when you can do it with CSS and JavaScript, because the server knows that you will ask for them anyway really, really well. Replaces all the inlining of initial HTML and JavaScript. Really, straightforward to implement. You do need to have HTTPS, even though the protocol itself says, well, browser can use non-TLS connection, but none of the browsers actually implement that, so you do have to have a certificate. The whole thing is just when you have a response stream, you push the image there with headers. And if a browser makes a request within 5 minutes with those headers, it will match, and it will get it right away. If you inspect the initiator in the DevTools in Chrome, you will see that some resources now have initiator push. So other means human, but push means the server actually pushed it to you before you ask for it. OK, the bad news doesn't work that well, because it doesn't actually play nicely with your regular browser cache. OK? And the whole reason here is, just let me go through these things, is that the server has no way of knowing that you already have these resources. There is a suggestion or open proposal to send a digest of the cache that you already have, so that the server will say, I'm not going to push it to you because you already have it. And if not, then I'll start pushing. So in my opinion, probably wait a little bit until this feature gets added. Otherwise, you're just going to kill the performance by pushing things that browser already have. HTTP2 was all about performance, and it's changing some of the best practices. If you compare what HTTP1, HTTP2, the best practices for domain sharding, concatenating resources, and inlining change. You still have to minimize the amount of work, like reduce DNS lookup. So the top part of performance advice is do less work. That applies always. Do good caching on the client side. But the rest, for example, split your resources to domains, now doesn't apply, right? Because you actually are more efficient having one connection that can be quality controlled and optimized, rather than separate connections that all compete, all do TCP congestion separately. Concatenation is now a problem, because that means if anything changes, the whole thing has to be resent. With HTTP2, you use browser cache and the same connection. So the 4 main features of HTTP to know is that it's multiplexed. That means multiple things go over a single connection. It uses compression, especially for headers. That's a big win. You can specify which resources should actually be sent faster by having preferences. And you have this new feature, resource push or server push, that can preemptively send things to the client. I have to admit that, except for server push, I think, people found ways to abuse all HTTP2 features, right, and kind of break it. But I think it's more a question of the technology is pretty new. The browser and the server stacks and code has not been hardened yet. So did not do enough validation. But I want to finish with something else. And I want to finish with a protocol called Quick. And we need this protocol just because HTTP2 has a very, very sore point, right? The original selection of TCP as underlying protocol means that if you have a stream, multiple resources are sent, if there is a packet loss in one particular frame, TCP says, no, you all have to wait until I actually send you this packet, because everything has to arrive in order. Okay? So that means for practical purposes, if there is a packet loss, HTTP2, which is perfect on paper for perfect conditions, as soon as you hit a couple % of packet loss rate, actually becomes slower. Because it doesn't open multiple connections, so it cannot actually be transmitting other things. It has to wait for that one frame, and then it has to continue. So if the choice of TCP was a problem because of order of packets, well, you have another choice, UDP. And there's a new protocol called Quick. And Quick is built on top of UDP. And of course, well, Google, who is developing Quick, had to build their own TLS equivalent. So Quick is almost like Speedy, the binary multiplex protocol that became HTTP2, but over UDP. And the main thing, it tries to optimize this latency, the number of round trips to actually start sending the data. So quick overview of a timeline of HTTP2. 1901, 26 years ago, HTTP.9 appeared. A year later, English Premier League, I don't know, but I think it's related. HTTP1 became standard 8 years later. 10 years later, Speedy became a thing, and now is deprecated in order to avoid kind of having two protocols that do the same thing and have different features. Now we have HTTP2, but the work on Quick has been going on for the last 4 years, right? So, the secret is that if you actually use Google Chrome and you visit Google properties, probably, most of the things are transmitted using Quick already. And you can kind of see if you go to, Chrome net-internals, there is a Quick tab. You can, if you have enabled, I forgot if it's enabled or not by default, but I think it's enabled already. You can see all the sessions that are actually transmitted not using HTTP1 or HTTP2, but Quick. And if you go then to, let's say, YouTube, you can see that these resources are transmitted using Quick protocol. If you inspect a resource, the response has a header called alt service that says Quick on port 443. The alt service is an interesting header. It says, OK, everything that you're asking me, it's also available on this different port. So you kind of say, for whole domain, I can also give you the same thing on this different port. So you're not saying only this resource is available. You're saying the whole thing is available. And that's to make things more efficient, so you can ask for many things at once. OK, how am I doing on time? 7 minutes. Great. OK, we only looked at HTTP2 and Quick, but I have to say that one of the most exciting things is WebRTC data channel. So we think of WebRTC as Google Hangout, video in a browser. But there is a data channel that you can communicate, and you can ask things from a server. And the problem it's trying to solve is that, let's say you have a server, you have a couple of users, everything is going great. As more users connect, the server slows down. You put more money, you buy a bigger server, but at some point it just crashes and burns. And if you watch Silicon Valley, it looks like this, right? It literally starts burning. Now, I'm not sure what they were doing and why they couldn't handle like 1 million users if they were just doing video compression. Are they doing video compression for every user? But WebRTC data channel allows you to actually bypass the server and connect peer-to-peer. That means browser to browser. And it looks like this. First user asks for things from a server, but then more users can ask each other. And as more users connect, you actually have more data available. Think BitTorrent. The more people actually using the service, the better it is, without increasing the load on the server. Completely flips, the financial or architectural decisions. And if the server goes down, not a problem. All the data is distributed and duplicate and should be accessible. We always think that offline means the server is down. No. Offline means I'm just asking for data from somewhere else. So people built a whole bunch of interesting projects using peer-to-peer alternative to HTTP2. OK, so we covered these interesting things. And I just want to quickly recap. There were several versions of HTTP2 protocol. And every version was trying to solve a problem that the real-world users of previous version encountered. And most time, you didn't know that you would have a problem when you actually started using that. So HTTP.9 was just trying to say, I want to load remote HTML documents. People started using that to load HTML documents, and then quickly found out, oh, we want to use it for everything else. It's so good. So HTTP1 was trying to solve, hey, we're trying to connect the whole world together. So let's design a better protocol for that. Ajax was trying to solve a problem. I don't want to load the whole page every time I need like a ticker update. Right? Can I load data without full page reload? And then WebSockets came along and says, hey, we want to communicate all the time. We want to chat. We want real-time data in a browser. And that's the problem that became apparent when Ajax long polling was not enough, and they had to invent something else. ServiceWorker today are trying to solve the problem of caching and offline and saying, we need full control over resources and how they're going to be cached and how they're going to be received by the browser. HTTP2 is trying to solve the performance. The World Wide Web was not built for web apps. Right? It was not built for a page that weighs like 3 megabytes and has hundreds of little things that need to be sent. HTTP2 is trying to solve this problem that wasn't apparent before. And finally, the Quick protocol is trying to find an alternative to the problems that TCP introduced. And I'm sure that tomorrow someone will invent new protocol saying, hey, whatever HTTP2 and Quick have done, here's a problem, and I have an alternative solution, and let's make this into a protocol. Let's make it into a standard. And I want to finish with this. The only things that don't go through this process, that don't suffer from defects, and that stay constant and not change at all, from day one are the failed things, right? Things that no one else is using. In that case, the thing is perfect. Thank you so much, guys, for listening. And I want to thank NDC Oslo and my company for sending me here. And don't forget to vote if you like it. If not, just tell me in person. Okay. Thank you.